Hello everyone, and welcome to the theory prep video on proof by induction, which is a new proof technique that we'll be learning today. So let's start with a motivating problem. Let's say it's the last day of CS 121 and Professor Boaz, because he's so nice, has decided he's going to give one candy bar to every student, basically. And he has infinite candy bars, so he's not going to run out, but he's decided to distribute them in a very specific way. So to make sure every student gets a candy bar, he has all the students line up in a big line. You can just imagine it keeps going this way. And he's going to follow two rules. The first rule is that Boaz will give a candy bar to the first student in line, or in this case, the 0th student in line, since we're indexing from 0. And then the second rule is that if Boaz gives a candy bar to student n, he will give a candy bar to student n plus 1. So if he gives a student a candy bar, he'll give a candy bar to the student right behind them. And he wants to make sure, well, if I follow these rules, if I follow the system, am I going to give a candy bar to every student? I think just intuitively, you think seeing these rules, well, yes, he will, right? But what if we want to prove that fact? So consider maybe this student, like the third student in line. How do we know that this student is going to get a candy bar? Well, we know by the first rule that this student is going to get a candy bar because this is the first student in line. And then by the second rule, since the 0th student got a candy bar, the 1th student will also get a candy bar, right? That's what this rule says. If student n gets a candy bar, student n plus 1 also gets a candy bar. And then by the second rule again, we know that the second student will get a candy bar, since we also know that the first student will get a candy bar. And since we know the second student, or student 2 will get a candy bar, and we know that by this rule, that means that student 3 will also get a candy bar. And so student 3 will get a candy bar. And this is, I think, this gives a concrete example of why every student will get a candy bar, right? So formally what we want to prove is that for any k in the natural numbers, right, because the students are indexed from 0 up to infinity or however many there are, we want to prove that any k in the natural numbers, the following predicate is true. And a predicate is just a proposition that depends on a variable. So it's basically like a proposition, but its truth value can depend on the variable. In this case, the truth value may depend on the variable k. So we want to check if the statement student k gets a candy bar is true for every single student, right? Because Boaz wants to make sure he gives all the students candy bars. And remember, if we go back to how we proved universal statements, the first thing that we did, the first step was always fix arbitrary k in the natural numbers, right? And so then we want to prove that this predicate, this statement, student k gets a candy bar, is true for that k. And we know that that'll be true because we can apply the first rule. So student 0 gets it, right? They get a candy bar. And then we can apply the second rule, k times. And what that will do is it'll go from student 0 to student 1 to student 2, all the way to student k. And that will mean that student k gets a candy bar. So thus, we've now proven that every student gets a candy bar. And so that's a fun example, but what exactly does that tell us about math? Well, actually, this is going to help us discover a new proof technique. Basically, in the previous problem, we wanted to prove this statement, student k gets a candy bar, for every single natural number, right? And the way we did it was just based on a couple of rules, we actually found that we could prove that the statement was true for every single k. So that suggests that maybe in general, if we have some problem and we want to prove that for any k in the natural numbers, some statement p is true of k, right? The statement in this case, in our example, p is student k gets a candy bar. Then maybe if we define rules similarly to the ones that we had in Boaz's example, we can actually, if we prove those rules, that's it. And that'll be sufficient to prove our theorem. So remember, our first rule was like the student 0 gets a candy bar. So maybe by analogy, we'll make our first rule p of 0, right? So that means that like the statement is true for 0. And then our second rule was basically for any natural number, if the nth student gets a candy bar, then the n plus 1 student gets a candy bar, right? So basically, if the statement is true for n, then the statement must be true for n plus 1. So we'll define our second rule the same way. For any natural number, if the statement is true for n, then the statement is true for n plus 1. And I claim that actually, if we just prove these two rules, then it will imply the theorem. And that's a nice proof technique, right? Because if you want to prove this theorem, you have to prove something for every single natural number. And that could be really difficult. And we'll see later an example of this. But if we figure out that these two rules are sufficient to prove the theorem, then all we have to do is prove the two rules. And the first rule is like just one specific example. And the second rule might be a lot easier to do because you're only working with you get to like assume that it's true for n, and then you only have to prove it for n plus 1 as opposed to just like trying to prove it for all n. So this seems like as a proof technique it might be helpful. So that's sort of the inspiration for the proof technique, but let's make sure that if we prove rules 1 and 2, that implies the theorem. And the justification will be sort of similar for what we did. So in the Boas example. So to prove theorem 15, we must prove that for any k in the natural numbers, the statement P is true for k, right? And if you remember again how we proved universal statements, the first thing you do when you prove a universal statement is you fix an arbitrary k in n, right? You fix an arbitrary variable that's in the set that you're considering. And now we want to prove P of k for that arbitrary k, right? And how are we going to do that? Well, again, we can apply rule 1. So rule 1 says P of 0, right? And then then I claim we'll just apply rule 2 k times. So if we apply rule 2 once, I'll just put a little 2 under this arrow to indicate that implication is from rule 2, right? So rule 2 for 0 says P of 0 implies P of 1. And rule 2 for P of 1 says P of 1 implies P of 2. And so we'll just keep going, and eventually that will imply P of k, which is exactly what we want. So that shows that these two rules imply that this statement is true for any k. Because remember, in order to prove that something is true for any k, well, if you fix an arbitrary k and then you prove that it's true for that k, then that proves that it's true for all k. So now we have a really nice proof technique because instead of having to prove something for all natural numbers, we can break it up into a couple like rules that are easier to prove. And so induction can definitely be pretty confusing, and that was a lot going on right there. So let's summarize what we've done. What exactly is the inductive principle? So the inductive principle says for P a predicate, remember a predicate is just a proposition that depends on some number, right? So a predicate could be like n is greater than 2. That would be a predicate. Because if n is like 20, then it's true. Otherwise, if it's like -1, it's false. Or like the predicate that we were using in the Boas example, right, is student K gets a candy bar. And in this case, this depends on K, and in this predicate, it depends on N. But so for any predicate on natural numbers, for any statement about the natural numbers, if we prove first that the statement is true for 0, and then we prove that for any natural number, if the statement is true for that natural number, it's also true for the natural number following it, then that implies that the statement is true for all natural numbers. And remember, it's the reason for this is just what we talked about earlier. It's basically like a domino effect. The first rule, this P of 0, we often call the base case, and that's because it serves as the base in our chain of argument, right? So this comes from the base case. And then the second rule we usually call the inductive step. That's because we apply it inductively over and over and over again until we get the result. And so let's apply the inductive principle to a problem, because I think this will help you see how to use it. But it's pretty important that you understand why it's true. I think that's the most important thing with any proof technique, is you should understand the reasoning behind why that makes a solid proof. So our example proof is going to be, we're going to prove that for any natural number, 6 divides n cubed minus n. So this symbol right here means divides. So it just means that there exists some m some integer m, such that 6 times m equals n cubed minus n. And so this, if we didn't know how to prove something inductively, this might be pretty difficult, right? It seems difficult to reason about how to 6 divide things, and also you have to prove it for all natural numbers, so it's unclear where you would even necessarily start. But let's go by induction. So first, remember the first thing that we have to prove is p of 0, right? So we have to prove the statement is true for 0. Well, we see 0 cubed minus 0 is just 0, which is divisible by 6. So now we've done the base case for the inductive proof, and now we have to do the inductive step, right? So for the inductive step, we must prove for any natural number, p of that natural number implies p of that natural number plus 1. Okay, so how do we do this? Usually what we say, remember, whenever we're, and I'll write down maybe what we're trying to prove here first. So we want to show, and we usually write want to show as WTS, for any natural number n, that if 6 divides n cubed minus n, then 6 divides n plus 1 cubed minus n minus 1, right? I just distributed the minus here over n plus 1. And so, again, we're going to use proof of universal statement here, right? So we're going to fix an arbitrary n in the natural numbers and assume, since we're proving an if-then statement, remember the first part of proving an implication is assume p and then prove q. So we're going to assume 6 divides n cubed minus n. And now we're going to try and prove q. So let's just take a look at q. So maybe the first thing we'll do is we'll expand it, right? Because we're looking for like terms like n cubed and n. So minus n minus 1. And if we expand that out, we get n cubed plus 3n squared plus 3n plus 1 minus n minus 1, right? So the 1's cancel, this n cancels with that, and that becomes a 2. And so to write it out again, we have n cubed plus 3n squared plus 2n. Let's make sure that 2 looks clear. And now we know n cubed minus n is divisible by 6. So if we subtract something that's divisible by 6 from this, and then we get something that's still divisible by 6, it implies that our initial quantity must have been divisible by 6, right? So we're going to subtract n cubed minus n. So subtract n cubed minus n to get 3n squared plus 3n, which we can just write as 3n squared plus n. And now we want to make sure that this is divisible by 6, right? Because if this is divisible, if this quantity here is divisible by 6, then this quantity here is divisible by 6 because we just get it by adding something that's divisible by 6, right? If we add n cubed minus n, then we get this other quantity. And since this is divisible by 6, it will preserve the divisibility. Great. So how do we know that this is divisible by 6? Well, we know it's divisible by 3, and so if this inner part is divisible by 2, then we can just pull the factor of 2 out, and then it'll be 6 times some integer, which by definition is what it means to be divisible by 6. So we want to show that n squared plus n is divisible by 2. And here we know this is true because we can consider if n is even, then we proved earlier n squared is even, so the sum is even, n squared plus n is even. And similarly, if n is odd, then n squared is odd, so n squared plus n is even, because when you add two odd numbers, you get an even number. Great, and so that implies that this is divisible by 6, which implies that this is divisible by 6, which is exactly what we wanted to prove. And now, you see we've proven the base case and the inductive step, and by the inductive principle, that means that this statement is true for every single natural number. So now we've finished the proof of the theorem. And that's a lot easier than what we were thinking of doing earlier, because earlier we weren't sure how we would go about doing this problem. And so that demonstrates sort of the power of the inductive proof.